Welcome back to the course on optimization. So, today we will solve some nonlinear optimization problem using GA and we will use R platform. So, let us see the problem that will be discussed in this particular class. The first problem is a maximization problem. So, it is a single variable function. So, the function is f(x) equal to x square plus x into cos x. So, the range for x is between minus 10 and plus 10. So, there are two optimal solutions. So, as you have seen on the graph. So, in this particular function there are two optimal solutions. So, you can see that there are two maxima and we will try to find out the global maxima between minus 10 and plus 10 using genetic algorithm, and the solution is x star equal to 6.560328. So, that is the solution. So, this is the maxima of this particular function and the function value at maxima is 47.70562. So, this is the first problem we will solve using genetic algorithm, and so this is the solution of this problem when we apply genetic algorithm, and you can see basically that all the population. So, it is at 100 iterations and we have given maximum iteration of 100 here, and you can see that at 100 iteration all the solutions are near the global maxima. And this figure is showing fitness versus generation curve, and you can see the base fitness, then the mean value as well as the median value, and you can see the with the progress of generation. So, with the generation that mean value is increasing and base value anyway. So, you got the base value probably at after a few iteration, maybe around 5-6 iterations. So, you got the solution of this problem, and then mean value of all these populations are increasing with the generation. The second problem is also a maximization problem. So, you can see, so again this is a single variable function. The function is f(x) equal to x square plus x into cos x plus sin x square plus x to the power sin x, and the range for x is 0 and 100. So, x is between 0 and 100, and if we solve this problem, so it has several maxima and several minima, and here we are trying to find out the maxima. You can see that there are several maxima of this particular function, and one of them is the global maxima, and genetic algorithm will give you the global maxima here, and the solution is x star equal to 94.26796. So, this is the solution and this point, and the function value at that optimal global maxima is 8980.96. So, this is the solution of this problem. So, we will solve this problem using genetic algorithm, and you can see here that if we apply classical optimization method here, so it is quite difficult or it is very difficult to get the global maxima of this or global minima of this particular problem, but genetic algorithm will give you the global maxima of this problem. So, we will solve this problem using genetic algorithm. Then this is the solution of this problem. So, you can see that at 100 iterations, so most of the population are at global maxima. So, this is the global maxima somewhere here, and you can also see that fitness the curve between fitness value and generation. So, you are getting the optimal solution probably at around 50 iteration, and this is also showing the mean value, how mean value is increasing, and at the end all the values are near the global maxima. So, this problem also we will solve using genetic algorithm. And the third problem is a multivariable problem. So, it is a two variable problem. So, the function is given here. So, you can see the function is a minimization function, or it is a minimization problem. It is a two variable function of x1 and x2, and f of x1 and x2 is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square, and range is minus 6 to plus 6 for x1, and similarly for x2 also minus 6 to plus 6. And there are, as you can see from this contour map, there are total 4 optimal solution and all of them are minima, and these solutions are given here. So, x star equal to, there are 4 optimal solution, x star is equal to 3 and 2. So, this is at the first quadrant, and then you have minus 2.80518 and 3.13132. So, that is on the second quadrant, and then there is another solution at the third quadrant, that is minus 3.779310 and minus 3.283186. So, that is on the third quadrant, and you have another optimal solution, and that is on the fourth quadrant, and the solution is 3.584428 and minus 1.848126. So, there are 4 optimal solution, and function value at all these optimal points is 0. So, therefore, this particular function has alternate optimal solution. So, function value is same, but the solutions are different. Okay. All of them are minima, and function value is 0 at all these optimal solutions. So, I have also shown you the surface plot. So, you can see, so there are total 4 optimal solution. So, this problem also we will try to solve using genetic algorithm. So, if you apply genetic algorithm, so you will get one of these 4 solutions. So, I have shown here the 4 solutions. So, you can see that one solution at the first quadrant, then there is another solution at second quadrant, another solution at third quadrant, and another solution at fourth quadrant. So, this is basically the solution obtained using genetic algorithm, and I have also shown here the fitness versus generation curve, and you can see that genetic algorithm is so powerful that it can get the, or it can reach the optimal solution probably after few iterations. So, here maybe after 10-15 iteration. So, genetic algorithm is converging at one of the optimal solution. So, now we will try to solve this problem using R software. So, I will show you, already you have learned what is R and how to solve the classical problem using R. So, today we will learn how to solve genetic algorithm using R. So, today we will solve some problem using genetic algorithm. So, now let us solve this problem using R. So, I have given the code here. So, only there are 14 or 15 lines code. So, I will explain all these lines one by one. So, first one, the first line is that I have to install the GA package. Okay. So, GA package is required, and the name of the package is GA. So, therefore, you have to install this package. So, as you know that you can install this package by writing install.packages and then GA. So, GA package can be installed, and I have already installed in my computer. So, I will not install it again, but if you have not installed, so you can execute this particular code and you can install GA on your computer. So, next is I have to include this library. Okay. So, to include the library, so you will write library GA. So, you will execute this code and you can install the library. So, I will execute it by clicking this run button. So, I have selected this particular line, and then I am executing this or I am running this one. So, library is included here now, and next is I have to write the function. So, here the function is written f equal to it is a function of x. So, one variable only, and this is x square plus x into cos x. So, this is the function. So, I am executing this particular function. So, now this function has been executed, and whatever you have executed, so you can see actually, so on the history here. So, the function is there, library has been included. So, next is just I would like to plot this particular function between -1 and 10. So, for plotting this one single variable function, so I can use the curve function of R. So, this is the curve function, and so you are using curve, and the arguments are, so f is the function. So, this function I would like to plot, and then this is between -10 and +10. So, lower bound and upper bound I am explaining here, and number of points you need basically. So, you can define, or otherwise whatever by default value will be taken. So, in this case I am putting 1 0 0 1. So, you can put some other value. So, if you are putting a large value, then your curve will be smooth, otherwise it may not be smooth. And then I am putting x level and y level of this particular curve. So, I am putting x level is x and y level is your f of x, and color I am defining blue basically. So, therefore, the curve will be of blue color. So, color you can define. So, now if I run this particular line, so just select it and just run it, then you will get this curve. So, you can see, so this is the curve I am getting. So, x axis is your x and y axis is f x, and there are two optimal solution. So, this particular few lines, so that this is I am just using to plot the function, and then I can apply genetic algorithm. So, genetic algorithm function is z a, and then I have to define some parameters here. So, if you want to see the parameters here, so you can go to help and just see what are the arguments of genetic algorithm. So, I can write help, and this is ZA, so you can see that right hand side you will get the genetic algorithm function. Okay. So, this is the ZA function. So, what you have to do, you have to define some parameters here something. So, you have to define whether you want to use binary coded, real coded, so that you can define, and similarly some control parameters. So, you have to define, then you have to define the fitness value. So, in this case fitness value is my f. So, I will define that one, and then you can actually define the other parameters population size, crossover probability, mutation probability, elitism. So, that you can define. So, anyway, so if you are not defining, then the default value will be taken. Here I have defined that I am using real value GA. Okay. So, I am not using binary value, but I am using real value, and my fitness function is f. So, this whatever function value, so that is actually I am defining as my fitness value. I am also providing the lower bound and upper bound. So, lower bound is 10 and upper bound is 10 here, and other values I am not defining here. So, whatever default value is assigned, so that has been considered here. So, now if I execute this particular line, so if I run this particular line, so GA will solve this particular problem and will try to find out the global maxima of this function. So, you can see, so let us run it. So, there are 100 iteration, and that is the by default value. So, if you are not giving, so iteration will be 100, and you can see that GA has been executed, and finally, it reached the 100 iteration. And now, I can see the results. So, results I can see from summary GA. So, you can see, so if I execute this one, then I can see the results. Okay. So, here you can see the GA setting. So, it is a real valued, then population size I did not change. So, 50 is the by default value, then number of generation again I did not change. So, that is 100 the default value, elitism is 2, crossover probability is 0.8, mutation probability is 0.1, and then lower bound upper bound I have considered minus 10 and plus 10, and finally, after 100 iterations, so I am getting the fitness function value is 47.70562, and the optimal value, that is the global maxima, is 6.560539. So, that is the your solution obtained, that is the base solution obtained by genetic algorithm. So, I am getting this solution, and I can also see the solution, the final solution using ZA at the rate solution. So, I can, if I execute this particular line, so I will get the solution. You can also see that one. So, this is the solution, that x 1 equal to 6.560539, that is the solution. Now, I can actually write a AB line. So, AB line is a function, so that will draw a line on the available plot basically. So, it will draw a line. So, I can write this thing. So, what I would like to draw a line at optimal solution, that means at 6.50539. So, I am just defining this is the vertical line I would like to plot, and this is equal to ZA solution. Color I would like to give red. So, if I execute this particular line, so I am getting the solution somewhere here, and that solution is 6.560539. So, I can also put the point optimal point. So, I can execute by putting points function. So, I would like to put a point here, and this is x axis is your ZA dot solution and y axis is the base fitness value. So, therefore, I am writing this is the x value and this is the y value, and then I am putting a round here. So, circular dot basically. So, PCH equal to 20 I am putting. So, if you are giving some other value, so some other shape will come, and the color I have used red. So, if I execute this particular line, then you can see that this is the optimal point actually. So, I am just putting an optimal point in this particular function. So, I am getting that one, and then I can plot GA. So, I will get the fitness versus generation curve. So, if I execute this particular line, so I will be getting fitness versus generation. So, you can see, so it is showing the base fitness and then mean value as well as the median value, and you can see that with generation the mean value of that means all the populations are actually converging towards the global optimal solution. Okay. So, this is the solution of this problem using genetic algorithm. So, as you have seen, so we have used ZA function here. So, now I can show you. So, I did not define many parameters here. So, I have only defined what type of ZA I am using. I have used real valued, and fitness function anyway you have to define, and I am using just upper limit and lower limit. But if you see that there are some other parameters, suppose I would like to use or I would like to change the population size. So, what I can do, that population size by default value is 50, but I would like to make it 100. So, I can make it 100 by just you increase the pop size, suppose this is 100, and then I would like to change the crossover probability. So, you just change the crossover probability, you define what is the crossover probability. Suppose I would like to give 0.9, and mutation probability, if I want to change it, suppose by default value is 0.1, and I would like to put a mutation probability of 0.05. So, this is the mutation probability I am defining, and maximum iteration, that is 100 by default value. So, but if you want to change it, you can change it. So, I can define that maximum iteration is suppose 200 now. You can also define the other parameters. So, let us run it. So, now the parameters are population size of 100, then crossover probability is 0.9 now, mutation probability is 0.05, and maximum iteration is 200. So, I am just running it again. So, you can see that now iteration is for 200. Okay. So, you can see from the summary ZA. So, if I execute this one, then you can see. So, now again real valued I have used. Now, population size is 100, then number of generation is 200. So, that is the generation, elitism is 5, and the crossover probability is 0.9 and mutation probability is 0.05. Anyway, so you got the solution. The solution is, I think we are getting the same solution, that is 6.56054, and the optimal solution is 47.70562. So, with this I can actually change the ZA parameters. So, depending upon what type of problem you are solving, if you want to change this parameter, so I can define these parameters here. So, I hope this is clear to you. So, we can apply genetic algorithm. So, this is just a one line your code. So, only what you have to do, you have to define the function, then you use the ZA function available in ZA package. So, this is just a 2 line, and other things are we are just plotting the function, we are trying to locate the optimal solution, something like that. So, other some function we have used, but you only need 2 lines, that is the function you have to define, and then you have to run or you have to execute the GA functions. This is quite simple to solve a nonlinear optimization problem using GA. And you can also define the GA parameters. So, within that function, so if you are not defining, the default value will be taken, but if you want to define, so you can change those parameters like crossover probability, mutation probability, generation, maximum iteration, okay, and then population size. So, all these parameters you can change. Now, for the same function, let us see how we can monitor the progress during GA iteration. So, we can also monitor how GA is converging towards the global optimal solution, or how GA is converging at global optimal solution. We can monitor that one, and that I would like to show using this particular code. So, only thing is that, so you have to use a monitor function here. So, I am explaining that one. So, I am not installing GA package here because it is already installed. So, I will just make a comment. So, I will not install that one. So, I will use the library. So, you execute the GA library, and then you have to write the function. So, already I have written this function. So, function, so I will execute this one. So, this is the function I have written already, and then I have to execute this particular line to draw the curve. So, I am just drawing this curve. So, using curve function. So, again it is x is between -10 and +10, and then I am putting label x label and y label, and color I am giving blue. So, I am getting this particular function. So, I think up to this line already we have discussed, and I think now you are familiar with these 2 lines. Now, next is that I would like to monitor the progress. Okay. So, monitor the progress of GA, or monitor the GA processes. Okay. So, GA processes I would like to monitor. So, now I would like to monitor the GA process, and for that I have to write this monitor function. Okay. So, I am explaining. So, here you are defining it as a function. So, monitor is a function, and this is a function of objective. And here, so first line is to plot the curve. Okay. So, this is the plot I would like to plot. So, this is the first line, and this is between -10 and 10. So, curve is already you have used. So, if you execute this particular line, this curve will be drawn, and then I would like to put the points, I would like to put the population. So, therefore, I am using the point function. So, this point function will put the points over this particular curve. So, here the population is given by objective population. So, within GA at the rate, so we will get the population. So, objective population will give you the population. This is the x axis value, and y axis this is objective fitness value. So, here in x axis this is the objective population, and in y axis this is the fitness value. So, I am putting that one, and then I am putting 0.8 PCH 0.8. So, it will give a shape. So, you can see that one, and color I am using 4, and then this rug. So, it will give you the location of this particular population over on the x axis. So, it will also show that one, and then when I am executing that one, because I would like to see the progress. So, system will sleep for 0.2, otherwise you will not be able to see that one. So, that is why I am just putting this one. So, what is happening? So, when you are running the GA function, this monitor function will be executed in every iteration. So, you can see that one. So, now I have written the GA function. So, now what is the difference? So, here I am using real valued again, the fitness value is f, lower bound is -10, upper bound is 10. Only difference is that now I would like to monitor the processes. So, therefore, I am writing monitor equal to monitor. So, here this is monitor is function. So, whatever function name you have given. Suppose if I want that I am changing this monitor to monitor 1, then in that case you have to write 1 here. Okay. So, this is basically using this one. So, I can monitor the progress. In the previous case I didn't use that one, so I have just solved the problem and I didn't monitor. Now if I execute this line, so it will also monitor the processes. Okay. So I can see that one. So let us execute this particular function, okay, that monitor function. So I am selecting this one and I am executing this one. So you can see on the right hand side, so you can see that monitor function is executed and it is stored as a monitor 1. Okay. So now I will execute this particular line. So I will run this particular line. So then the ZA will run, and along with that I can see the processes. Okay. So how ZA population is converging towards the optimal solution. So that I can do, just see. So you can see that one. So initially the population is between upper bound and lower bound, it was uniformly distributed, and with the iteration you can see that population is converging at global optimal solution. It is showing the generation, now it is 46, 47 like that. So you can see this is the global optimal solution and all these populations are trying to converge at global optimal solution. So it will run up to 100 generation because we have defined maximum iteration equal to 100. So now you just see, so this is the solution we got, and you can see whether we got the solution. Just I can see that summary. So this is the solution you got, 6.560556, and I can see the ZA solution. So summary you can also see the other things. So we have used real value, then population size 50, number of generation 100. So crossover probability, mutation probability we didn't change, so default value has been taken, and finally you got the solution. And then ZA solution you can see what is the base solution you got, and solution is 6.560556, and I can write a AB line, vertical line. So using this particular line, so this is the solution here, and I can also locate the point using this. So this is the optimal solution obtained by ZA, that is the base solution obtained by ZA, and I can also execute this particular line to see the generation versus fitness curve. So if you execute this particular line, if you plot ZA, so you can see fitness generation versus fitness value. Okay. So that has already been defined. So now by using this monitor function, you can monitor the movement of the population. So how it is moving towards the global optimal solution, so that you can monitor using the monitor function. So that I have shown here. And so but if you want to just solve the problem, and then you only need to execute the ZA function. Okay. So as I said, this is only a 2 lines code. So you can just write the function and then use the ZA function to get the solution. The other lines are basically to see or to plot the function, then to see the optimal solution, to monitor the optimal solution, something like that, but that is not required. If you want to get the solution, just you run your objective function, write your objective function, and then you run the ZA function. Okay. Now I would like to solve the second problem. So second problem, as you have seen, so that is also a maximization problem, and we have lot of local optimal solutions. So several local optimal solutions are there, and we will use ZA to get the global optimal solution of this particular problem. Okay. So this is the code I have shown here. So here you have to include the library. So already ZA has been installed. So just include the library, ZA library, and then write the function. Okay. So let us execute this one, the first line. I have included the library here, and then you run the second line, that is the function actually, and then I can plot the function using curve function. So I am just plotting it. So you can see that there are several optimal solution. Okay, several optimal solution, both minima and maxima. So these are all maximum points, and one of them is the global optimal solution. So we will apply ZA here, and here I would like to monitor the convergence of the population, how population is moving in different generations. So I can monitor that one. So I have written the monitor function here. So I just put the curve function just to draw this one, then I am putting the points. So this is the population I am putting, and then I am also looking at the value at x axis. So, I am putting RAG function, and then system will sleep for 0.1. So, this is the monitor function. So, let us execute this one. Okay. So, I have executed this monitor function, and then now you execute the ZA function. So, I have just used, so this is the same function. Here I have used lower bound is 0 for this particular problem and upper bound is 100, and I would like to monitor the processes, okay, monitor the progress. So, let us run this particular line. So, you can see that initially populations were between upper bound and lower bound, and with the progress of iteration, okay, so with the generation, and all these solutions are converging at global maxima. So, you can see the global maxima is somewhere here, and this is the solution I got, and finally, you can see that ZA summary, and so solution is 94.26678. So, this is the point actually 94.26678, and I can write I can see the ZA solution. So, this is the solution 94.26678, and I can draw a vertical line using AB line command. So, this is the vertical line. So, this is the solution, final solution I am getting, and I would like to locate the optimal point, and this is the optimal point somewhere here. So, this is the optimal point, and similarly I can also see the generation versus fitness, okay, fitness versus generation curve. And here you can see that ZA could converge at optimal solution probably at around 35 after 35 iteration or something like that. So, you got the optimal solution, and after some iteration actually all the populations are near the global optimal solution. So, using the monitor function, so we can monitor the population, how these populations are moving towards the optimal solution, so that we can monitor using monitor function. So, you can see that how ZA is converging at global optimal solution. For the second problem, there are several local optimal solution, but ZA could identify the global optimal solution. Just see if you are applying the classical optimization method. So, classical optimization method will give you only one local optimal solution, but ZA is capable of finding the global optimal solution of this problem. So, now let us see the third problem. So, third problem, as I have shown you already. So, it is a 2 variable problem, and we will try to find out the optimal solution of this particular problem, and here all of them are local optimal solution, means function value is same for all of them. So, function value is 0, but we call it alternate optimal solution. There is no global optimal solution because the function value for all of them is 0. Okay. So, function value is 0. So, therefore, it is not that one solution is better, other one is inferior, all of them have same quality, that means same solution, objective function value is same for all of them. So, therefore, if you are applying ZA, so you will get one of them. So, you will get one of these solutions. Okay. So, let us see, let us try to solve this problem using ZA. So, here this is a multivariable function. So, I am writing multivariable ZA. So, you have to include the ZA library. So, just include it, and then first I would like to plot the function. So, these few lines are just to plot the function. So, here I am just writing the function. So, that is FP. So, the function to plot, and it is a 2 variable function. So, therefore, x1 and x2, and the function is x2 plus x1 square minus 11 whole square, then plus x2 square plus x1 minus 7 whole square. So, this is the function. So, let us execute this one. So, I have executed this particular function, and then I am defining what is x and y. So, x and y is between minus 6 and plus 6. So, I can use the sequence, okay, SCQ, that sequence. This is minus 6 to plus 6, and then the points will be created at an interval of 0.1. So, this is for true for both the cases, that means x1 is varying between -6 and +6, and similarly x2 is also varying between -6 to +6. So, let us execute this particular line. So, I can see basically, so this has been executed. So, now if you want to see what is x1, so this is the x1 values. Okay. So, you can see that -6 to +6 and at an interval of 0.1. Similarly, x2 also I can see. So, this is the x2 value. So, this is -6 to +6. So, now I would like to find out the function value at each grid point. So, for that I am using outer function. So, this is the outer, that x1 and x2, and fp function is taken, and it will calculate the function value at each grid point. Okay. So, now let me execute this one. So, you can see, so this is the fp result. Okay. So, here, so it is not showing all these points, but you are getting the function value at each grid point. Suppose this is 1 1, then 2 2, then 3 3, like that, 1 1 1 2 1 3, something like that. So, you are getting the function value at each grid point, and then to plot this function. So, I am using this particular function which is available in R. So, PERSP. Okay. So, this is the function I am using to plot this. So, this will give you a 3D plot of this particular function. So, it is x1 and x2 we have to define, we have to give. So, this is x-axis is x1, then this is x2, and this is the fp value of this particular function. And then this theta and phi will give you horizontal angle and vertical angle. Suppose in this case I am putting 30 and 30. So, if you want to have a different view, so you can change this angle. I will also show you. Then expand, I am using 0.5, and color I am using light blue. Okay. So, therefore, if you are executing this particular line, so you can plot this function. Okay. So, I have plot this particular function. So, this is the 3D plot, and if you want to change your view, suppose I want to use 45 degree and 45 degree. So, horizontal and vertical angle I can change it. Okay. So, this I can change, and maybe I will get a different view. I am getting a different view. So, this is the 3D view of this particular function, but I would like to see the contours. Okay. So, for that I can use the contour function. So, contour function is, the arguments are x1 x2, then the function value you have to put, and number of levels. So, I am defining 100. So, if you are not defining, the default value will be taken, and here also I am I would like to give blue color. Okay. So, therefore, if I run this particular line, so I will get the contour map. So, you can see from this contour map. So, there are total 4 optimal solution in each of the quadrant, that is first quadrant, second, third and fourth quadrant, and once you are applying ZA, so you will get one of them. So, this particular line, so far whatever I have executed, so these lines are just to plot this particular function, but now I will execute the ZA. So, for applying ZA, so you have to write a function in terms of x. So, I cannot define x1 and x2 here. So, x is an array, and between we have x1 and x2. So, therefore, this is x1 and this is x2. So, I have to write this function in this way to implement that one. So, I cannot write the function like this x1 and x2. So, only thing I have to put x. Okay. So, therefore, I am writing this function. So, this is the function of x1 and x2. So, this is x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. Then, so this is the function f. So, let us execute this particular line. So, I am getting this particular function. Now, I am running the GA function. So, I am not putting the other parameters of GA. So, what I am doing? So, I am using the real value GA and function is f. So, this is a minimization function, and therefore, I am putting minus sign here. Okay. GA is solving a maximization problem. So, therefore, as this is a minimization problem, so I am putting minus. Otherwise, if it is a maximization problem, you need not put minus sign here, and so I am getting this one. Then the fitness value is f. So, this is a maximization problem now, and then you have to define lower bound and upper bound. So, lower bound is minus 6 and minus 6, that means for x 1 it is minus 6, for x 2 also it is minus 6, and upper bound is plus 6 and plus 6, and population size I have defined 100. So, if I do not define, then default value will be taken. Okay. So, therefore, let us run this particular line. So, it is iteration up to 100. So, this is the default iteration value given. So, 100 and population size taken is 200. So, I did not change the other parameters like crossover probability, mutation probability, elitism, those I did not change. I have taken the default value, and after that I would like to locate the point. So, anyway, so I can run this particular line. So, but this is already plotted. So, therefore, I try to put the solution. So, I am using again point function. So, now it is a 2 variable. So, therefore, this is the solution x 1 and this is the x 2 solution, and then PCH I am taking 20, that means I put a circle and the color I am putting red. So, therefore, if I execute this particular line, so I am getting this particular. So, J is giving this solution. Okay. So, then I can see the summary J and J solution. So, this is the summary, and you can see that I have used real value, population size is 200, iteration is 100, number of generation is 100, elitism is 10, crossover probability I did not change. So, this is 0.1, 0.8 and 0.1, and the solution so this is upper bound and lower bound of x 1 and x 2, minus 6 and 6, minus 6 and 6 for x 1 and x 2, and you are getting the solution. So, it is not exactly 0, but it is around 10 to the power minus 3. So, you can also define this precision, but whatever solution you are getting 3.00 and 1.99, but exact solution is 3 and 2. So, you are not getting the exact solution, but you are getting close to the optimal solution, that is 3.002. So, this is you are getting, and this is you are getting 1.99. So, we are getting one solution. Now, if I execute this one for the second time, maybe I may get this solution, or I may also get the other solution. So, let us see that if I execute these particular lines, so second time, so let us see whether I am getting the same solution or I am getting the different, I am getting a different solution. So, I am getting a different solution. This time you see that I got a solution in the second quadrant. So, let us run it again. Yeah, I am getting on the first quadrant, again first quadrant, again first quadrant, so I am getting the solution on the first quadrant, but so you may get the solution in the other quadrant also. So, what I can do basically, I can also get the solution by changing this upper bound and lower bound. Suppose I would like to get the solution of the second quadrant, then what I will do, so for lower bound this is minus 6 and upper bound of x 2 I am putting 0 here, sorry lower bound I am putting 0 and upper bound of x 1 I am putting 0 and lower bound of that I am putting 6. So, what will happen now, I have used the upper bound and lower bound of the second quadrant. Okay. So, minus 6 and 0 and this is 0 and 6. Okay. So, in that case what I should get the solution in the second quadrant. So, you can see that one whether I am getting this solution on the second quadrant. So, let us see. Yeah, I am getting the solution on the second quadrant. So, similarly you can also change this thing. So, in order to get the solution at the third quadrant, so let us put that x 1 is between minus 6 and 0 and x 2 is also between minus 6 and 0, and if I execute these particular lines, then I should get the solution at the third quadrant. So, similarly, I can also get the solution at the fourth quadrant. So, fourth quadrant, this is x 1 is between 0 and 6, 0 and 6, and x 2 is between minus 6 and 0. So, let us execute these particular lines. So, I am getting the solution at the fourth quadrant. So, therefore, by changing this upper bound and lower bound, so I can actually get the solution at different quadrant, but if you are giving between if you are giving this range between minus 6 and plus 6, you will get one of the solution. Like the single variable function, I can also monitor the solution in case of multivariable function. Let us see how we can monitor the GA iteration. So, here for this particular function again, that is x 2 plus x 1 square minus 11, then plus x 2 square plus x 1 minus 7 whole square. So, for this particular function, so I would like to put the monitor function. Okay. So, that I will do. So, as you have seen, so first part is just to plot this particular function. So, I am not explaining again. So, I have written the function, then I am defining x 1 and x 2, then I am calculating the function value at each grid point using outer function, and then I am plotting it the 3D plot using PERSP function, and I can also plot the control lines using control function. So, you have to use library. Okay. So, library is GA. Now, let us execute these few lines. So, just to plot that one, plot the function. So, I am getting the 3D view as well as the contour plot. So, I am just plotting here. So, we are, and then I have written this monitor function. So, in this case, so earlier monitor function, so we have used curve because that was a single variable function, but in this case I have used contour. So, here we have two variables, that is x 1 and x 2. This is the function value, then number of levels, control levels I have used 100, then color I am using blue, and then I am also defining what is x level and y level, and then in the main I am writing, or I would like to write the generation. So, that I am doing here, and then I am putting the population, that using points function. So, in this case there are two variables. So, therefore, first one is give you the first variable, this is x 1, and I am writing comma 1, that means first variable for all rows, and similarly for second variable for all rows. Okay. And then PCH you are using 20. So, it will give you circular shape, and then color I am using 3, and then system will go for sleep for 0.1. So, this is the monitor function. So, let us execute this. So, this is the monitor function I have the monitor function I have executed, and now I have written the function, the fitness value, and then I have used the GA. So, in this case, so I am just using monitor equal to monitor, then other part is similar. Okay. So, you can see that it is a real valued fitness function is f, then lower bound and upper bound I have defined, population size I am using 100, but you can change it, and now I am putting monitor. So, I would like to monitor the progress, okay, monitor the iteration. So, let us execute this one. So, you can see the population all over the search space, and with the progress of iteration you can see that it will converge at one of the optimal solution. So, I think in this case it will converge at the first quadrant solution. So, just see. So, it is converging the solution at the first quadrant. So, you can see that initially all these populations were uniformly distributed all over the search space, that is between -6 and +6, and finally, it is converging at one of the solution. So, you can see, so it will go up to 100 iteration, and so we got the solution. Solution is somewhere here, and just to plot the solution, so I have used the point function. So, I would like to plot the final solution. So, you can see that this is the solution, final solution we got, and if you want to see the value, so I can use GA summary, and GA summary will give you everything, that is what type of setting you have used. And then if I run this particular GA solution, so I can see the solution. So, the solution is 3.00 and 1.99. So, as you know that you will get the near optimal solution, exact solution you may not get, but I hope this is acceptable to us. So, we got this solution, and maybe if you are running it for the second time, so we may get other solution, but we may also get this particular solution. So, let us see. So, just see whether we are getting the same solution or we may get some other solution. So, probably we will get the solution at the first quadrant itself, and you can see that with population initially the solutions were uniformly distributed, but over the iteration it is converging one of these 4 solution, and now converging at the solution on the first quadrant. So, but you may get the solution at the other quadrant also. So, these are all alternate optimal solutions. So, therefore, J will give one of them. So, in this case also, so we will get the solution at the first quadrant. Yeah. So, you can see that we got the solution at the first quadrant itself. Okay. So, we have applied GA in 3 problems. So, 2 single variable problems and 1 multivariable problems. You try to solve this problem using R. So, I will also give you the R code. So, you try yourself to get the solution. So, in the next class, so we will solve problem with constraint. So, I will explain how GA can handle a nonlinear problem with constraint, and GA is very efficient in handling constraints. So, that I will explain in the next class.